Talk about. We can actually talk. We didn't have homework. No, we just worked with boss. Yeah.
Feels like this class is just. It's all
Okay, I need y'all to get out the 3 handouts that I gave to you last class. They should be numbered as 109, 110, and 111.
No.
You can borrow one of those other erasers. Thank you. Okay, so today we need to finish up the linear part of the next unit. So we're in a little different spot than my other classes, so I'll have to get you guys to remind me. But I'm going to do about the 2-3 minute review of 109. That's the one we went over together last time. So just kind of a vague refresher about what we expect you to remember about linear stuff and some of the stuff that got sprinkled in that you may not have seen before. Then we'll do this. I'm sorry. I still couldn't hear you. I'm sorry.
Yeah, like do you have any course classes left over? Eclipse classes.
I don't know where they're at right now. If you want to come back, I'll look later. Sorry, I don't know right now. Okay, and then I think you guys didn't get quite as far with worksheet 2. I could be wrong there, so you'll have to tell me when we get to that one. And then to finish up the linear stuff, the 111 is a worksheet where I picked out the 3 question types that students usually want a little more extra practice on. And so I will reteach each of those one more time and have you do one more extra guided practice with those. So everything we expect you to know from linear is summarized in these 3 worksheets. And then we'll start moving on to quadratics. So we'll only get partway through that one today. So the 3 minute review of what we talked about last class is we had the first 4 questions where we needed to write the equation of the line. So I reminded you what slope-intercept form was and tried to sell you on point-slope form. And to write the equation of the line, we need slope, which you could count rise over run or use the slope formula for. So I reminded you what that was. Then on questions 1 through 4, we used the slope formula because we had 2 points. And then I plugged in the first point and got the equation. In question 2, we had to remember a couple things about vertical and horizontal lines so that we knew that that one had a slope of 0. In question 3, we had to remember what you need to know about the slopes of parallel and perpendicular lines so that we could do that one. 5 and 6 were two questions that were new for most people, but if you could do questions 1 through 4, you can do question 5 and 6 as long as you know these two things. Direct variation always goes through the origin, even though it doesn't come out and tell you that. And instead of calling it the slope, we call it the constant of variation. But same slope formula, we'll still find the constant of variation. And as soon as you're given this point, it gives you lots of options like questions 1 through 4. This is one of the 3 topics we'll practice even more on the last handout. On the back page, question 11, we talked about how to change something to slope-intercept form. So solving it for y equals puts it in mx plus b format. So we may ask you to do that like a question 11. And you may want to do that for a question like 7 because that's an easy way to graph it. If you put it in slope-intercept form, you should be able to see the y-intercept was -4 for point 1, and then use the slope 2/3 to get a second point, and then you can sketch in your line. Number 8 was a vertical line. I could tell by the equation type. Number 9 was a piecewise function. This is the second type that we will get a little more practice on today, even after worksheet 2. But basically I graphed y equals -4, kept this piece of it, graphed y equals 3x minus 2, kept this piece of it, and graphed y equals 2 and kept that piece of it. And that's pretty much it, as long as you can do it carefully. Question 10 brought up what the absolute value of x looks like, really for the last question, but if you know what absolute value of x graph looks like, this was just shifted right 1. And then the third type of question we'll practice on worksheet 2, but also a couple more on the extra practice worksheet, is changing an absolute value into a piecewise function. So I use this one kind of as an example because I feel like this one's easier. But the stuff under the absolute value was part of your piecewise. The opposite of the stuff under the absolute value was the other part of your piecewise. So I did the same thing here. The stuff under the absolute value was one part of your piecewise. The opposite of that was the other part of the piecewise. This one we could see it was switching at 0. This one we had to put some more thought into it. But I sketched a quick picture. We saw that they were switching hands when y equals 0. So you could either set this equal to 0 and solve, or this equal to 0 and solve. You're going to get the same number. You're going to get that that occurs at 1/3, which is why I broke it up around 1/3. This one was to the right when it had a positive slope. This was to the left when it had a negative slope. So again, I know that's just a very quick reminder, but we're going to dig deeper on those type on some of the other ones. Now, my other classes had time to practice all of this worksheet 2. Did y'all have time to start this? I don't remember. I think y'all were a little bit behind the other classes. Do y'all have worksheet 2 finished? You do not have it finished. Okay. Then I need you to practice these so that you can see what you actually still remembered and what you were able to pick up on from worksheet 1 when we went over it last class. So I think there's a lot of value in that, so I'm going to set a timer here. I'll give you 15 minutes to go through it, and then I will share my answers and we can discuss the ones you want to discuss. So again, that's a little bit behind the other classes, but we'll be caught up. Should be caught up by the end of the week. But for right now, please work through worksheet 2 and at least figure out which ones you're concerned about. About 4 more minutes. Was 15 minutes, so I apologize if that was not enough time for you to do it at the pace you would like to, but at the very least it should have shown you where you were kind of slowing down and what things you might need to pick up on. So I'm going to quickly go over all of it, and then I'll try to pause in each little question type to let y'all speak up if there's something I'm going over too quickly here. So all of worksheet 2 is just like worksheet 1, except for questions 1 and 2. 1 and 2 were not on worksheet 1, but this just means go plug in -3 into F and see what you come out with. So 18 minus 1, you should have gotten 17 for number 1. And then 2 times, plugging 1 in, ends up being 2 times 1, which should be 2. Those two look okay? I need y'all to double check my work. If y'all disagree with anything, speak up right away, please. Okay, the next 4 questions are about writing the equation of a line. So again, I'm personally going to do point slope just because I think it's the easiest. So I'll do question 3 and 6 at the same time just to show you that they're really the same thing. So I've got a point. I can plug the y value in for y1, the x value in for x1, and I've almost got my answer. The only thing I don't have is my slope. Can do the same thing with one of these 2 points. Y minus the y value equals the slope times x minus the x value. Same thing. Number 6 is also almost done. I just need the slope. So you could visually make a graph, plot these 2 points, and count rise over run, and that would always work. It's just a little tedious. It's always going to be a little bit smarter to just subtract the y values to calculate your rise, and then in the same pattern subtract your x values to calculate your run. Looks like the slope should have been -4/3. So that's one possible answer there. Again, if you really wanted to do it in slope intercept, that's okay too. You just need to make sure that's okay, that it's equivalent. Okay, down here I could subtract the y values and then subtract the x values in the same pattern. Looks like the slope is 4/3. I guess the only thing I'd probably do different on question 6, -0 doesn't really do anything, so I personally wouldn't leave that as part of my answer, but that would be the point slope. And if you really just are determined to add the 4 over, that would be okay too. That would just be slope intercept instead. Okay, number 4 is also about the same amount of work. If you know point slope and you know where to plug in the x value and the y value, you're almost done again, but this time instead of giving 2 points, they tell you that it's horizontal. So you need to have memorized that horizontal lines have a slope of 0, and then since this is all times 0, I would probably add the 5 over and then quit there. It's also helpful to know that horizontal lines always have this format: y equals the number. This one, to go through -4, 5, it needs to go through y equals 5. Okay, and then for the 4th time in a row, if you know point slope and you carefully plug in the y value and the x value, the only thing that really takes a minute is thinking about the slope. So for this one, last time it was perpendicular, so I took the opposite reciprocal slope. This one's parallel. If you want lines to be parallel, they need to have the same slope. That guy has a slope of 2, so I want this guy to have a slope of 2. Okay, so all 4 of these kind of get grouped together, and we need some of these same skills for questions 7 and 8. So is there anything about 3, 4, 5, or 6 you disagree with, or you want to ask a clarification question on, or anything I can do to help with that? Okay, then 7 and 8, again, these 2 I realize probably feel a little less comfortable, but we'll practice. I will go over one of these again on the next handout and have you practice one more of these as guided practice for just a tiny bit more practice. But for direct variation, again, there's only 2 things you have to know about these, and then they shouldn't be harder than the last 4 questions I just looked at. Direct variation, by default, always goes through the origin, and instead of calling the slope the slope, we call it the constant of variation. Oops, not variable, variation. Now I don't know the background to that. I don't know why this is the case, but those are the only 2 unique things. So now question 7 says write an equation, and I've got 2 points. So I can do like up above. I can plug in the y value and the x value and the point slope, and then I have everything except for slope. But if I've got 2 points, I can use the slope formula to figure out the slope is 7/3. Now I chose to plug in 3, 7. If you would rather plug in 0, 0, that's the same thing. So there's more than one way. to make your answers look. All right, number 8, same thing, except this one has 2 questions. First off, this one asks for the constant of variation, which again, I know it's just a key term for slope. So if it's direct variation, it goes through the origin, and they're telling me when x is negative 1/4, y is 2. So I can subtract those in the same order using the slope formula. Just remember that dividing by negative 1/4 is the same as multiplying by his reciprocal. So negative 8. That's the first answer. The constant of variation, the slope, was negative 8. Again, not doing anything different than slope formula that I haven't already done 6 times on this one worksheet. But then the other question, find the y value when x is negative 3. So you could really approach this a bunch of different ways, but I think the easiest way is to just make the equation of the line, even though it doesn't tell you you have to do that, because you've got a point, 0, 0, and you now know the slope. So if you know the equation is like a formula that's going to tell you all the points on that line. Y is always going to be negative 8 times whatever x is. So if x is negative 3, y should be 24. So that was your other answer there. So again, we'll practice this one more time on the next handout, but if you have an immediate question or something I skipped over too quickly, I'd be happy to clarify now. Anything you want to ask about 7 or 8?
On 7, I got the answer that you got, but on the answer key it says y equals 7/3 of x. So like, is that still equal or no?
Yeah, so what they did is instead of plugging in 3, 7, they just plugged in the other point. And since subtract 0 doesn't do anything and subtract 0 doesn't do anything, this is the same thing as this.
Okay.
They look different, but they're the exact same thing. It doesn't matter which point you plug into point slope. 0, 0 does kind of clean up nicely, but I'm still trying to emphasize point slope, so I kind of want those pieces to be there. Okay, on to the back. I'm actually going to skip down to question 13 first, because switching something into slope-intercept, that's mx plus b. You can tell that's not my favorite form, but it is a useful form for when it's good. And basically, you just need to focus on this is y equals. This is not y equals. Subtract the 2x over and divide everything by negative 3. And now it is in terms of y equals, specifically y equals mx plus b. And you often do that when you want to graph it in a calculator. Your calculator wants it in y equals format. So. Now, the reason why I skipped down to do this for question 13 is that's what I would do for number 9. Graphing this one is not my favorite, but if I simply solve it for y equals by subtracting the 3x over and multiplying both sides by negative 1, now it's in mx plus b format. I can instantly tell you where the y-intercept is, negative 6, and I can use the slope to get a second point. Count up 3, right 1, and really you only need 2 points to define a line, but if you use the slope multiple times, your line might look a little bit better. So I'm going to go up 3, right 1 a couple times. So I think the best approach for that one is put it in slope-intercept, graph the y-intercept, use the slope for a second point at least, if not a third or fourth point. Number 10 should be one of the easiest ones. Y equals, or x equals a number, it's going to be a vertical line, and so if it's x equals negative 4, it's got to be the vertical line that goes through negative 4, where all x values are always negative 4 regardless of what y is. Number 11 is the piecewise function, and this is one that students tend to struggle with. But again, you're just keeping pieces of certain lines. Y equals 4 is a horizontal line. but you should have only kept this part of it, where x is equal to 3 or greater than 3, which would be that. The next one is in mx plus b format. So he looks like this, but you should have only kept this part of this line. Less than 3, that's an open circle, but greater than -1, another open circle, and x can be the values in between, not the values to the left of -1, not the values to the right of +3. And if you can do those two, you can do it one more time. Y equals -2, another horizontal line, but only keep it where x is equal to -1. That would be a closed circle, or less than -1. That would be the stuff to the left, not the stuff to the right. That's what you should have been aiming for in number 11. Now again, since sometimes this is something that students don't feel the most comfortable with, just an option, just a suggestion. When this says f of x, that means we're talking about a function, and a function has to pass the vertical line test. So if your graph didn't pass the vertical line test, there was no way that could have been the correct answer. Mine does pass the vertical line test. This hits the line at least once, or at most once, but even, and most importantly, at x equals 3, it hits once, here, not here, and -1. It's here, but not there. So that's a quick little check. Okay, and then the last of the graphing questions, which is really, I think, trying to push you in the right direction on the last question. You really need to know this parent function. Actually, there's, I don't know, about 8 or 10 parent functions, and I can tell you guys from my calculus classes that if they remembered some of those parent functions, some of what they've been doing would be a lot easier. In fact, I have a logarithm graph up here from their class the other day. They didn't remember what that looked like, so then they couldn't finish a question, even though they could do the calculus part. So anyway, so if we know what absolute value of x looks like, we just need to pay attention to the transformations. Subtracting 2 directly from x would shift it right 2. So you should have ended up with something like that. All right, and then on to the last question, which is probably the hardest, just based on you've probably never seen it before until I showed it to you last time. But I'm going to go over this same thing again on the next handout with the extra practice. But I think the best way to understand this is to use an example that you should know, like the absolute value of x. This one's a little easier to change into a piecewise function, but this one we can follow the same pattern and kind of steal the process. So, absolute value of x, sometimes the equation is y equals x. Sometimes the equation is y equals -x. Now, how this helps me with question 14 is that sometimes it was the stuff under the absolute value sign. So that's going to be true here too. The stuff under the absolute value sign is one of the equations, 3x minus 4. And then the other equation is the exact opposite of the stuff under the absolute value sign. Because all of this could be the negative version, and then the absolute value turns around and makes it positive. So I need the opposite of the stuff under the absolute value sign. Opposite of the stuff under the absolute value sign. And then do it over here. The opposite of the stuff under the absolute value sign. Negative 3x minus 4. Or if you want to distribute, negative 3x plus 4. But you need parentheses if you don't distribute. Over here, it's a little easier to see that this switches at x equals 0. You just need to be careful that you put the inequality signs correct. So the part with the positive slope is to the right, and the part with the negative slope, purple, is to the left of 0. And then to make sure that we actually hit this point and there's not an open circle there, you need to either include this or this, but not both. Doesn't matter which one you include, but we need that point. So I've got to find that same point for this function. Now, even with the terrible graph here, this is going to shift some to the right. So I've got part that's a positive slope, part that's a negative slope. But if you force yourself to make a picture, you're going to see that right down here, that's the y-intercept, I'm sorry, x-intercept. So that's where y is 0. So you could either set this equal to 0 and solve to get 4/3, or you could set this equal to 0 and solve to get 4/3. Both lines are in the same place when y equals 0. So that's how I know 4/3 is the dividing factor here. And then again, you got to be careful with the inequality direction. Positive slope is to the right, negative slope is to the left, and to make sure you include this point, you need to include one of these. Not neither, not both, but either one, doesn't matter.
And that's for the greater than or equal to, just that little line under the...
Yes.
Okay, gotcha.
Yeah, you need to include it, otherwise nobody ever hits this point and it would be an open circle, and we want to do that. So we're going to practice 2 more of these on the next handout. So again, make some growth there, but it's fine if you feel like you still need a little bit to go. Okay, I did not pause for any questions on this whole back page, but is there something, a step of any of this that I went over too quickly that you want me to say again or ask about? Okay, then let's move on to the extra practice. So this is where I picked out 3 question types that I just feel like you're less familiar with: the direct variation, the graphing piecewise functions, and making a piecewise function from an absolute value. Same thing, some of the same things we just did on worksheet 2, but this one just focuses on these. So I'm going to reteach these from scratch one more time for questions 1, 3, 5, and 6, and then I'll give you a few minutes to try one last time for 2, 4, and 7. Until we get to the test review, I don't have any extra practice on this for you. This stuff is out of the textbook, the very first section in the textbook though, so I guess we don't have a textbook assignment for you from 1.1 unless we decide to add a day to the unit or something, but you could still go do that if you needed to. Okay, so again, you just need to follow me one more time. Half of this can be notes, half of it will be guided practice. Alright, so I see direct variation. I know it's going to go through the origin, even though they're not going to tell me that. And instead of calling the slope, they're going to call it the constant of variation. Those are 2 things specific to this question type. So if I want to know the constant of variation, I'm really just seeking out the slope. He goes through 0, 0, and he goes through -1/2, 4. Plug those into the slope formula. Dividing by -1/2 is the same as multiplying by the reciprocal. Looks like that comes out to be 8. No harder than just using the slope formula. Just a different name. Second half of the question, find the y value when x is -5. And again, there are other ways to do this, but to me the most direct way is to just make the equation, plug in the point like 0, 0, plug in the slope that you already found, and then you've got a nice clean equation, and the equation tells you all the points on the line. All the y values will be the same as x times -8. So when x is -5, y would have to be +40. So similar work, similar thought process, slope formula, point slope, etc. But you have to know those highlighted parts to be able to do direct variation questions. So I'll have you practice that on question 2 in just a minute. Okay, graphing piecewise functions. So again, what I would do if you feel like you struggle with this is just graph all 3 of these. Graph y equals 5. Graph y equals 2x minus 5. And graph y equals negative 6. And you're already halfway done. But this doesn't pass the vertical line test, so this cannot be a function. I haven't used the restrictions yet. Now I just need to carefully read these. My red line should only exist when x is equal to 4. The equal to makes it a filled in circle, and greater than 4. The greater values would be to the right, not the stuff to the left. I'll skip to the bottom one. It's supposed to be y equals 6, but only when x is equal to negative 2. The equal to makes it a filled in circle, and less than negative 2, which would be the stuff to the left, not the stuff to the right. And then the middle one, which is purple for me, is supposed to exist between negative 2 and 4. He doesn't get to equal negative 2, so that's an open circle. He doesn't get to equal 4, so that's an open circle. But he can be the values in between those. Not the stuff to the left of negative 2, not the stuff to the right of positive 4. Now it's finished. And notice now it passes the vertical line test. So it really is a function, as it implied based on its name. Calling it f of x implies it's a function. So making sure it passes the vertical line test is just a quick way to guarantee your answer is wrong if it's not that. Okay, and then on to the third one that we're going to do a touch more practice on before we can finally move on to quadratics. So I'm going to do 5 and 6. Again, I know I already did this one just a minute ago, but I really feel like this is the key to understanding how to set these up. Absolute value of x is a parent function that you need to know what it looks like. One part of the function comes from the stuff under the absolute value sign. One part of the function comes from the opposite of the stuff under the absolute value sign. I can do the exact same thing on question 6. Part of it's going to be the stuff under the absolute value sign. Part of it's going to be the opposite of the stuff under the absolute value sign. I'm already halfway done. This one, I can see where it switches. X switches at 0, positive slope to the right, negative slope to the left, and include one of the points so that you get this point. Over here, I don't know when it stops being this function and starts being this function. But if I graph it, and it doesn't have to be accurate, but think about adding the x is going to shift it to the left. It's still going to look like a V. Where it stops being the negative slope and starts being the positive slope is right here where y equals 0. So you could either set this equal to 0, 2x plus 1 equal to 0, and solve and see that that happens at negative 1/2. Or you could set this one equal to 0. It doesn't matter which one you do because both of these are in the same place at the same time when y equals 0. You're going to get negative 1/2 either way. Then be careful that you've got your inequalities pointed the right direction. Positive slope, I want to the right. Negative slope, I want to the left. And to make sure we include this point, you need to include one of the two, but not both. Alright, so do you guys have anything you'd like to ask about those 4 examples before I have you try one more of each type? Okay, then take a moment, do 2, 4, and 6. Also try to do those questions without looking at the examples But if you need to look at the examples, that's fine too, but try to do it without, if possible. Then we'll check that, and then we can move on and put a dent in the quadratics handout. Get a little bit closer to getting caught up with everybody. here's my answers to number 2 and number 4. If you look down there at the bottom, I've got 3 and 9 for the first question. And then the piecewise function was all above the x-axis, which is why I could show it at the same time. Okay, and then try to zoom out a little bit. Here's my answer to 4. Oh, I can't show that one yet. I'll leave this one back up for a second. There's 4. And 6. Part was 4x minus 2. Part was the opposite of that. And you had to put some thought into where it was switching, and that was at 1/2. Again, I wish I had a lot more practice for this so I could have you practice this again. There should be a few questions on the test review, but I really feel like, especially this page, any hints, any notes you might want to give yourself when you look back at this in a week or two before your test, anything that would help you, remind you what you needed to do or what mistakes you were trying to make, would probably be beneficial for you. So I will give you a minute to round that out. And then I'll jump over to today's. So while you finish that up, so again, we've got like 3 topics that we do in this little mini unit. So one topic is linear. Everything that we will expect you to be able to do is found on those 3 handouts, 109, 110, and 111. And we'll also spend about a class on quadratics. So we're going to focus first on solving quadratics and then graph analysis. That'll be for another day. But unlike the linear, this should all seem familiar to you. I shouldn't be saying anything new with the quadratics that you didn't already learn in Algebra 2. I realize direct variation, graphing piecewise functions, and making piecewise functions from absolute values you probably didn't learn or did very little of. Alright, so on the front page of this, we're going to talk about the 4 different methods and when you could use each one of these to solve quadratics. Now, as I say solve in this, solve implies you're trying to figure out where y equals 0. So, kind of like we did on the other worksheet, I'm going to go through one of each of these with you. So I'm going to do 1, 3, 5, and 7. And I'll give you a few minutes for you to try the same process in 2, 4, 6, and 8. And then I'll tell you how we're going to dig a little bit deeper after that. Alright, method 1 only works if you've got a quadratic, so that means the exponent is 2, but notice that there's no x's to the first. Most of the time you have a quadratic, you usually have some x squareds and some x's. But if you only have x squareds, you can just use normal solving stuff, like undoing subtract with add, undoing times 2 with divide 2, undoing a square with the square root. But you need to realize that quadratics have 2 solutions. Sometimes it's the same solution twice, but usually it's 2 unique solutions. What I'm most concerned about with this method is from here to here. When you take the square root of both sides, you have to remember plus or minus. 9 is only one of the answers, -9 is the other answer. That's one of the things that us as math teachers, I know you've heard that 1,000 times, but it's still a common mistake. So, if it's a quadratic that doesn't have x's to the first, you can simply do that. Just make sure you do plus or minus when you square root both sides. Alright, method 2, solve by factoring. Oops. This is my favorite, because to me this is one of the quickest and most usable of all the methods. So if I'm trying to solve this, if it factors and if I can factor it, whether that's guess and check or slowing down and doing the product sum method, we get something that looks like this. Now this only works with 0. 0 is a special number in this sense. If I can make this times this have to be 0, I could make this be 0, and I could care less what this is, because 0 times anything is 0. Or I could make this be 0, in which case I could care less what this is, because 0 times anything gives me 0. So it gives me two simple equations to solve, and it looks like the two answers to that quadratic would be 10 and -9. So if you were good and quick with factoring and reliable with factoring, usually that's the method you want to use the most. Okay, method 3 doesn't apply to our class so much, but this would be totally fair game on the ACT. If they asked you to solve this and you had a calculator, you could graph it. I'm graphing it on my calculator over here. And it's a quadratic that looks like this-ish. But here's the key to know what to look at. If we're trying to solve this, implying that where it equals 0, so where y equals 0 is also known as the x-intercepts. So your two answers are right here, bless you, 4 and -5. The two times where y is 0. So that's can be as fast as factoring, but you don't have to risk missing the factoring. But that only is a smart strategy when you have a calculator. So let's review the three methods we've currently talked about and get to the last one. Method 1 is pretty easy, doesn't require a lot of new knowledge, but it only works if you have x squareds and no x's. Method 2 works out great, but only if it factors. Not everything factors. Method 3 works great if you have a calculator to quickly graph it, but it also depends on the answers too. If this was like 4.18765 and you needed to be more accurate, your calculator may not be the best, but it does give you, if the answers are nice whole numbers, it gives them very quickly. Which moves us on to quadratic formula, which is what most of this handout is going to be about. This is by far the most important, because this is the method, the only method that always works. If you only know one way to solve a quadratic, it has to be quadratic formula, because sometimes you don't have a calculator, sometimes it doesn't factor, and sometimes it's not in the right format to use method 1. So these first two will work out pretty nicely, and then as we get into the third page of this handout, we'll look at some messier ones. But in a quadratic formula, this is what you need to remember. You need to know where the values a, b, and c come from. A is the coefficient of x squared, b is the coefficient of x, and c is the constant. You have to memorize the quadratic formula. Honestly, memorizing the quadratic formula should probably be the hardest part of this. Everywhere there's a b, I'm going to plug in my b, which is 8. B squared, I'm just going to change that to 64. Everywhere it says a in the formula, I'm going to put a 4. Everywhere it says c in the formula, I'm going to put a 3. And then it wants me to put 4 in place of a again. Okay, down here in the denominator, this is easy enough for you to do without a calculator. 2 times 4 is 8. This part is going to vary quite a bit. This stuff under the square root, this is called the discriminant, and this is probably the most important part of the quadratic formula. The discriminant determines how many and what type of answers you get. If the discriminant's 0, you get the same answer twice. If the discriminant's negative, we get 2 imaginary solutions. And if the discriminant's positive, depending on what positive number it is, depends on what kind of work we've got to do. Now, just to play it safe here, I don't know, 4 times 4 would be 16, times 3 would be 48, 16 minus 48 should be 16. So, to be honest, most of the time I would probably throw that in the calculator to be safe. Now, the reason why we've got 2 pages, front and back, on this handout is it really just depends on this determinant. Square root of 16 works out great, so this doesn't take much effort, but it's not always going to be this clean. Square root of 16 is 4. So one of your answers comes from -8 minus 4 over 8, and the other one comes from -8 plus 4 over 8. Then when you reduce those, you have found your 2 answers. Now again, if it was up to me, I probably would have just factored it, because that would have been a lot faster for me. But we've also got to practice quadratic formula so that we can do it when we need to. So go ahead and finish copying that one down. And then what I think you should do is look back at question 1, think about why I was able to do that, and then you apply it to question 2. Look at question 3. Look at what I did on question 3. You try to do the same thing on question 4. Look at what I did on question 5 with the calculator. You graph it in your calculator, see if you can get the answers for number 6. And then finally, steal my work on number 7 and try to replicate it on number 8. Just try the one quadratic formula for now. So I'll give you about somewhere between 10 to 15 minutes. So try the rest of that page. And then we'll go over it so that you can make corrections if you need to.
So we have like a band performance during Thursday advisory. Can we come in on Friday, like during
The testing.
Atlas?
I'm given the Atlas testing, so I can't.
Okay.
Not that I want to be, but
Oh, well, so what should?
so next Tuesday would be the next time.
Okay.
See what happens. Okay, so this okay, so 2 plus 1 x
That was fast.
I like this version. It's simplest.
Oh. For sure you got those right now?
It's simplest.
How come you're not done then?
It's not fast. Yeah, but simplest. No. It's only 20 acres. Actually, it's 9 times. 19.
think it's some. Is that where you get 19 ingredients? Yeah. It's been a while. I didn't think it's been monotonous. 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 Why? 10 minutes. 10 minutes. Monotonous. Close enough. There's just so much nuts. Those take like 2 seconds.
I think you got for 111. I was a little bit behind, so.
The last question.
I just want to see what you got.
That's what I got for a final answer. That's fine. I included it here, but it didn't matter, so that could go either way. So that part's fine. You need to check the others.
Yeah.
Here was 4. That looks good. And then 2.
I got that wrong.
Which one?
Number 2, because I got negatives.
Your slope was negative. What did you...
So I plugged it in there for slope. I plugged in -1.
Oh, okay. So you're plugging the values in. That's kind of unusual. I guess that should work though. Y... I mean, it is the slope formula. This is y minus y, x minus x. You divide this over, divide all this over. You get -1 over -1/3. Well, a negative divided by a negative
Just positive.
should be positive, so
Okay.
yeah, you just have an arithmetic mistake there. And if that was a +3, this would be a +9. So you just need to double check that part.
Cool. Thank you.
Okay, let's do about 4 more minutes for this front page. That will be 11 minutes total that I gave for you.
What's 4 times 29? 29? Okay, it is 160. 4 times 29 is 160. It's 4 times 30 is 120.
Are the graphing questions, are they necessary to have a calculator, or is it possible to do it without? Just didn't know if I needed one for that. You think it'd be easier?
I mean, it depends on how much you remember about graphing.
Yeah, I didn't know if it was gonna be asked on a test, if we'd need if we'd be allotted a calculator for that or not.
Well, we probably just wouldn't ask you to do it by graphing.
Gotcha, okay.
So, like, one thing you could do, again, and we're going to talk about this more next class, but there's a formula to find the vertex, which is this point down here at the bottom or the top part. And the x value comes from the opposite of b over 2a, which is really just like the left side of the quadratic formula. So if we did that, that would be -1 over 2. Well, the vertex is always in the middle. So if -1/2 in the middle, you can kind of think about how far would you have to go to get to this point is how far you'd have to get to this
Gotcha.
point. So
Okay.
in a
Gotcha.
roundabout way, if you know enough about graphing, you can avoid, you could figure out what the graph looks like without using
Okay,
your calculator.
gotcha.
But that's pretty extreme though.
Okay.
I don't feel like that's
Gotcha.
a big deal.
And you said we might cover that next class, or?
Yes, graph analysis we'll do some next class.
Gotcha.
Alright. So let me share my answers and make sure that you don't need to do any corrections here. But for question 2, you could have gotten away with just adding the 125 over, dividing both sides by 5, and then taking the square root of both sides. Just make sure when you take the square root of both sides, you did plus or minus. 5 is the answer, but so is -5. You don't want to lose half of the answers from one step. So, perfectly fine to use this method, it just doesn't come up very often. Number 4, I asked you to try this one with factoring. So, again, if you need to slow down and do product sum or some other method you learned in Algebra 2, then please do. But once you got it factored, this equals 0 at 3, and this equals 0 at -1/2. Factoring should be the slow part of that question. Alright, number 6 was by graphing. So this was fine to throw in your calculator. Again, we probably won't put one of these on your test because we probably will want to see what you can do without a calculator. But when you threw this in the calculator, it looks like it crosses the x-axis at 4 and 7. 4 and 7. These are where y equals 0. And if you're solving this, you're trying to figure out where y equals 0. So 4 and 7.
How
And
would
if
you find that on a calculator, or is it better to do it without this question?
well, I mean, I just threw this graph in my calculator and looked at the graph.
Okay, gotcha.
Yeah.
Fine.
Yeah, that's all I'm aiming for there. Okay, and then on to the important one, which again, we're going to practice this more, so it's okay to struggle with this one some. But quadratic formula, the first half of quadratic formula should not be giving you an issue. Knowing where A, B, and C come from, you need to re-memorize the quadratic formula if you forgot it. That's going to be big on the ACT anyway. Easily the most important formula you get out of Algebra 2. The next step shouldn't be a problem at all because we just plug it in as it says. It says plug in a B here, plug in a B again. I'm going to go ahead and use my calculator. 19 squared is 361. Plug in A here, C there, and A again. Make sure that you notice C is negative. If you put in a 7 instead of a -7, that's going to be a problem. Now, depending on these numbers, depends on if you need a calculator or not. The denominator you shouldn't need a calculator for. But the discriminant, I totally understand why you might want to put that in the calculator. I'm not trying to get you to do 4 times 6 times 7 and then add that to 361. So we could give that to you on the test, but we would need to give you more reasonable numbers. But I'm just going to throw it in the calculator. It tells me that is 529. Now, I don't recognize that perfect square, but it is a perfect square. And honestly, I only know that because I did it with my 8A classes yesterday. That comes out to be 23. Again, that would be calculator. I don't expect you to know what 23 squared is. Now, you still need to get your two answers out of this. This is telling you what to do, but this is not good enough. One answer is going to come from -19 plus 23 over 12. Another answer is going to come from -19 minus 23 over 12. And then those will reduce. 4 twelfths is 1/3. -42 twelfths, we could divide both of those by 6. So -7/2. That's the two answers you were looking for. Now again, I probably should have told you when and where it was fine to use a calculator, but I highlighted that here. I threw all this in my calculator to tell me that was 159, and then I asked my calculator what's the square root of, or I'm sorry, 529, and then I asked my calculator what's the square root of 529. Again, we can do quadratic formula, but if the numbers are super big, we're going to let our calculator do that part. But I knew what A, B, and C was. I knew what the quadratic formula was. I plugged in A where it told me to. I plugged in B and C where it told me to. Calculator, calculator, adding, reduced fraction, subtracting, reduced fraction. Takes a little bit of practice to feel comfortable, but you guys can certainly do that and need to be able to do that. Okay, so the reason why this isn't just a one-page handout as we move into the rest of this is the discriminant, the stuff under the square root, can vary widely. The square root of 16 came out to a nice 4 and made this easy to finish this question. Over here, even though I didn't know it off the top of my head, the square root of 529 comes out to a nice whole number because apparently 529 is a perfect square. But sometimes the discriminant's not a nice whole number. So on the next page, we need to review how to simplify these radicals. So when they're not perfect squares, we know how to change them up. And so this is pushing us, making sure that we have the background to do the harder quadratic formula questions. So the first row, I'm going to do the first 2 rows for you, and I'm going to ask you to come back and do the last row here. But the first row should be pretty easy. These are ones that you probably just have memorized without thinking about them. At least I hope. But if we slow down and think about why these are 5, 4, 10, and 7, it's going to help us with these other ones that don't come out perfectly. The square root of 25 is 5 because I have two 5s under the radical. 25 is the same thing as 5 times 5. 16 is the same thing as 4 times 4. 100 is the same thing as 10 times 10. And 49 is the same thing as 7 times 7. So what you need to notice is because we have two of the same numbers under the radical, we are able to pull those out of the radical. And it's kind of like when we talk about x in math, there's a lot of what's called, people like to call it invisible math. When I say x, it's implied we're talking about 1x to the first. There's numbers there that we just don't write every single time. With square roots, there's an index. It's an understood index of 2, which is why you need two of the same thing to pull one out. Now, I'm going to show you two ways to do number 13. I'm going to show you the way that I like, and then the way that your algebra teacher may have shown you, but I'll tell you why I prefer my way after I show you both of them. So my way is I do what's called the prime factorization, also known as factor tree. So I'm going to split 125, and I'm going to just try to think of two numbers that go into 125, like 5 times 25. If it's prime, you stop. If it's not prime, you have to split it up too. So instead of calling it 5 or 25, I'm going to call it 5 times 5. So apparently 125 is the same thing as 5 times 5 times 5. That's what we call prime factorization. The prime numbers that multiply to a number is this prime factorization. And since this is a square root, I need two of the same thing to group up so that one of them can come out front. And then this 5 had nobody to pair up with, so he got left behind. And the square root of 125 is the same thing as 5 square root of 5. Again, I know this seems random, but we've got to make sure that we can simplify these correctly for later quadratic formula questions. That's the way that I like to do this. And the reason why I prefer this method over the other method that your other algebra teacher may have shown you is this method works great when you start doing cube roots and fourth roots and fifth roots. If this was a cube root, I would just need 3 5s to group up and bring one out. If it's an 8th root, I need 8 of the same thing to group up and bring one out. So splitting it up into its prime factorization is very versatile for other type of roots besides square roots. But technically, the quadratic formula is always a square root. So technically, you can get by doing this. If you can think of a perfect square that goes into that, like this, 125 is the same thing as 25 times 5. And you might split it up that way because this reduces to 5 and then this doesn't reduce, and you end up with the same answer. So, do y'all remember last year if Mr. Smith, Ms. Polson, did they show this way to y'all? They did? Did they show the factor tree, prime factorization way? Okay, they showed both. Okay, so again, this is fine for doing square roots. It's going to be harder for you someday when you need to do cube roots and fourth roots. That's why I'm going to focus on this method. Okay, so square root of 27. 27 is like 3 times 3 times 3. So I got to take groups of 2 to group up and come out front. Everything that's out front gets multiplied together. Everything left behind gets multiplied together. 8 is like 2 times 2 times 2. 2 of the 2's can group up to come out, and there's 1 2 left behind. The square root of 8 is the same thing as 2 square roots of 2. And 12 is like 2 times 2 times 3. So I can pair up the 2's, bring him out front, and then there was a 3 that had nobody to pair up with, so he got left behind. Square root of 12 is the same as 2 square roots of 3. Now, this might be more information than you care to know, but one thing that I used to do when I was in high school as a way to check, this doesn't guarantee that you simplified it correctly, but it will tell you if you messed it up. when you have a calculator, if you type in the original question, if it's not a perfect square, it's going to be some crazy decimal. But then when you get your answer, if you're willing to type it in, it should be the same crazy decimal. So if you thought this reduced to 3 square root of 2, you can see these are not equivalent. This can't be the answer. But if you thought the answer was 2 square roots of 3, you can see they are the same decimal. So again, that doesn't guarantee that you simplified it fully, but it does guarantee that you didn't mess it up at least. Because we're just changing the appearance, we're not changing the size. Okay, so in just a minute here, I will ask you to do 1 row of those and a couple rows of these so that we can, we're still going to be a little bit behind, but that's okay. So the other part is that in the discriminant, sometimes it could be a negative number like this. And this is where we get the idea of imaginary numbers. So this is the one you need to memorize. The square root of -1 is where the number I comes from. I feel like we haven't talked about imaginary numbers yet this year, so just in case we haven't, please make sure that you understand imaginary numbers are not imaginary. The mathematician who did publish the work and got it published in some paper or book thought they were imaginary because he didn't know any uses for them at the time, but we have lots of uses for imaginary numbers, but the name had already stuck. Notably, everything with circuit boards, computers, cell phones, none of that stuff exists without imaginary numbers. It just has a misleading name. Now, if you can simplify radicals, then this is just adds 1 step, and I suggest you do this step at the beginning. If you have a negative under the square root, bring it out as an I. Just do it right away. The square root of 4 is still going to be 2. Negative under the square root, bring it out as an I. Square root of 9 is still going to simplify like normal. Negative under the square root comes out as an I. Square root of 81 is still 9. You're just adding that 1 extra step. You're pulling out the negative. Let's do one of these harder ones. You're pulling out the negative, preferably at the beginning so you don't forget about it, and then simplify the square root of 216 with whatever method you prefer. So my one more cell for the factor tree is that 216 is a big number, but factor tree actually makes this very manageable. Because if I can think of one number that goes into 216, the number gets smaller and smaller and smaller and smaller and smaller. It gets easier and easier. The first one's going to be the hardest. So apparently 216 is the same as a 2 times a 2 times a 2 times a 3 times a 3 times a 3. That would be his prime factorization. I've got 2 2's that can group up and come out front. I've got 2 3's that can group up and come out front. I have the I that's out front. I've got a 2 that got left behind and a 3 that's left behind. Everything that comes out front gets multiplied together. Everything left behind gets multiplied together. The square root of negative 216 is exactly 6i squared root of 6. And that's about as hard as they can get. But factor tree and just pulling out the negative as an I is all you need to be able to do. Now again, when I see you guys on Thursday, we're going to be doing some quadratic formula questions where we've got to simplify the radical like this, which is why you need to practice these. So you've only got about 6 minutes of class, but what I need you to do for some extra practice here is if you would please finish this row 17 through 20 and finish this row 26 through 28. If you would please do those 7 questions so that you'll be ready to check those on Thursday, and then we will continue with quadratics and hopefully finish with quadratics on Thursday. But if we don't, it can trickle in the Friday if need be. And you are welcome to practice more than that, but you don't have to.